The topic of this video is electron configurations, and this video is gonna show you how to do the electron configuration and what is exactly going on behind it. Okay, we know that the electron configurations is a distribution of electrons in the atoms or in the ion, and we can figure it out through the ionization energy, and which is the energy to pull out the electrons away from the atoms, and we can use the Coulomb's law to quantify the ionization energy. And as we know, like most atoms has multiple electrons, so they are multi-electrons. And since they're multi-electrons, then it organizes different shells and subshells and orbitals. And all these shells, subshells, and orbitals has the similar ionization energy. And okay, so what's interesting is that the inter part of the electrons is called the coin electrons, and the rest outside part is called the valence electrons. And once the coin electron was filled up, and they will provide a shielding force that shielding the attractions from the nucleus to the valence electrons, so which lowering the ionization energy. So this is how the shielding works. Okay, so let's look at the first and the most simple example of hydrogen's atoms, which has positive protons and negative electrons. So the Coulomb's law allows us to quantify the force between the charges, the positive and negative charges, and it came down to the charges and the distance between the two charges, which is the radius. So how can we figure out the force to pull out the electron away, which is the ionization energy? So firstly, we say that the protons is a +1 charges because it has only one proton, and the electron is a -1 charges since it only has one electron. So we multiply the two charges together, and then what else do we need is the radius, which is the distance between the charges. So here came out a really interesting question for hydrogen and helium's atoms. Which one has a higher ionization energy? Okay, let's look at the graph of the hydrogens and heliums. So from here we can all notice that the size of helium is slightly smaller than the size of hydrogens. That's because the helium has one more protons than the hydrogens, which provides a greater attraction to the surrounding electrons. Therefore, make the size smaller, and by this it means that the helium has a higher ionization energy than the hydrogens. And now, for the atoms of helium and lithium, which atom has a higher ionization energy? You might immediately think about that the lithium will have a higher ionization energy. However, the thing's different because we can find that for the first shell there could be only 2 electrons. So once we add one more protons in the nucleus and one more electron surrounding, there will be forming a second shell, and there will be a shielding between the first and second shell, which lower the ionization energy, make it really small. Therefore, the helium actually has a higher ionization energy. Okay, let's look at this chart. It is a chart showing the ionization energy of the first 20 elements. So we can first draw some boxes, and which represents the orbitals. With each box represents orbitals, and the letters and number under it shows like the shell, what the shell is. So we have 1s, 2s, 2p, and then 3s. So we put for hydrogens, we can know there's only one electron, so we draw one arrow in it pointing up, so we know like hydrogen has only one charges between. So, and then for heliums, we get one more atoms. I mean, excuse me, we have for helium has one more protons and electrons, so we put one more electrons in the same shell, which make it a higher ejection, so higher ionization energy. Then there's a big filling between the helium and lithium. That's because we add one more shell between. Once we add one more electron to it, we have one more shell to the electron shell, which lowering the ionization energy. Then between the berylliums and lithiums, it makes sense that it increase the ionization energy, but the weird thing is between boron and beryllium, because it get one more electron, which create one more shells, then it get low. It make ionization energy become lower. Then it makes sense that the carbon and nitrogen will increase the same way. However, there's difference between the nitrogens and oxygen, because once you fill all three boxes with one electrons and you get one more to it, then you get two electrons in the same orbitals, which is spinning in opposite directions, which create the repulsions that lowering the ionization energy. Then we add one more protons and we get fluorine and one more to neon, and all the same. It's going in the same trend. So let's get into the electric configuration. So we first know that there's 4 energy level, which is S, P, D, F. That's the 4 subshell, and name in the quantum mechanical. And the S sublevel has 1 orbital, which means it can have 2 electrons, and P has 3 orbital, which means 6 electrons, and D has 5 orbitals. Then it can hold 10 electrons at the same time, and F, which has 7 orbitals, then it can have 14 electrons. So we draw from 1 to 7, which is 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Then we starting from 2p, right next to 2s, and 3p, 4p, 5p, 6p, and 7p. Then we move from 3p to 3d, then 4d, 5d, 6d, and 7. Okay, excuse me. and 70, but technically there should be no 70, so we don't need to use the 6F, 70, and 7F. So, and the rules is like we draw a diagonal arrow from the top right to the left bottoms, which is the correct way to read the arrangements of this energy level. So we get 1s first, then we go 2s, then 2p, then 3s, and then 3p, and 4s, and 3d, then we go to 4p, and 5s, then we go to 4f, no, yeah, we go to 4d, then 5p, then 6s, then we go to 4f, 5d, 6p, 7s, then we go back and forth, that's how to write, how the arrangement to write the electron configuration. So 1s, 2s, 2p, 3s, 3p, and it keeps going like that. And once you're writing electron configurations, the only thing you need to do is just put the number of electrons for each sub-level on as a power number. So then, okay, so it keeps going like from 1s and starting to the last electron you have, and by this rule we can get all the electron configuration without knowing the periodic table. And for example, if we're doing a Mg magnesium which has 12 electrons, so we're starting from 1s2 which has 2 electrons, then 2s2, and then there's 34 electrons, then 2p6, p sublevel can have 6, and then we need 2 more, which will be 3s2. So that would be the electric configuration of magnesium, which is 1s2, 2s2, and 2p6, 3s2. And we've noticed that the electric configuration for neon, the noble gas, is 1s2, 2s2, and 2p6, which is exactly the same front part of the magnesium. So we can simplify the magnesium's electric configurations as the neon 3s2, which is an easy way to recognize. Thank you for watching the video, and I hope these videos can help you with your understanding of the electric configurations.